So, ladies and gentlemen, welcome to this final lecture of the short course on seismic isolation. So today we will try to summarize all the issues that we have analyzed through all these lectures, and especially we will try to compare the results for the analysis returned by the finite element model of the case study structure. And we will consider actually all the isolation systems that we have actually designed and then implemented in our model. And there will be some comparison, with the numerical simulations that we have done yesterday with within the MATLAB environment, just by using very simple analytic expressions for the hysteretic response of the implemented seismic isolation systems. So as I mentioned in the lecture of yesterday, I've sent the final homework to you via email. You will see that it is a very simple exercise about what we have seen about the pre-design of the isolation systems, and the deadline for that, for the successful conclusion of this webinar is next Tuesday at 6 p.m. So you can just very briefly describe the overall procedure that you apply, just very briefly in a brief report. And that's it. You can send it through the email rather than maybe upload in a shared folder. But I think that the final file will be not so much big. So if there is no question about what we have seen yesterday and generally what we have discussed up to now, and I think up to now means the overall short course, we can directly start by analyzing the outcomes of the finite element model returned by SAP 2000. So is there any question? Okay, so I share my screen and let's start by analyzing all the outcomes. So I will open directly the software SAP 2000 so that we are able also to see the results of all the analysis. I have performed them this morning, and actually the total runtime was equal to half an hour approximately, and I think that that was a little bit longer just because I opened all the three models together, and I've run all of them together. So maybe the time duration was a little bit longer, but you see 30 minutes is a very short time for nonlinear time history analysis. Generally, there are softwares which can consider also much higher run times. For instance, I know depending obviously on the complexity of the structural systems that you consider. But then I think that for what we have modeled, it was a fair enough runtime because half an hour for actually three models with the 7 nonlinear time history analysis, okay, +1, but for the gravity load application. But you have seen that the gravity load application is a very fast nonlinear time history analysis simply because it is just a gravity application. So there is no movement, but just some flexural deformations for the elements, and that's it. Actually, there is no involvement for the nonlinear leaks, which is actually the only nonlinearity that we have implemented within the software. So let's start by seeing all these results. So I will start with the first model that we developed, so with the curved surface slider devices. So we have already seen how to see results in terms of time series of a given response parameters. And I just show again we have to go to display, show plot functions, and this is the window that we obtain within the software. So we have to choose the proper load case, and you see now we have the whole set of natural events in terms of nonlinear time history analysis. And I just you to see some graphical results for the displacement time series. And if you remember, we considered this point, which was actually a corner point for the plate, for the reinforced concrete plate. And this was just because we can choose whatever point at the same location for the isolation system, just because we are not expecting to find a significant torsional behavior for the isolation systems. Since okay, in this case, it is quite more truth because this is the curved surface slider isolation system. So this particular typology of devices allows to have a very negligible behavior from the torque, I mean the torsional motion of the overall system. But especially we will get exactly the same behavior also for rubber bearings and lead rubber bearings. And this will be the main result of our definition of the isolation layer. I mean, if you remember, our main rule to install isolation devices when we deal with the rubber bearings with and without lead core, we have to pay attention on placing the isolation devices at the edges of the overall system, so that we are maximizing the torsional stiffness of the isolation layer. And actually in this way, so the distance between between all the devices and the stiffness centroid can be the maximum one, and so the stiffness is maximized. So let's have a look at the, okay, again, a quick one. This was the waveform, let's say, the results in terms of time series of displacement at the isolation level. And you see that here we have the maximum one, which is 116 millimeters. And yesterday I remember that, okay, here we considered two strategies for the analytical modeling of curved surface sliders. If you remember, we implemented both the hyperbolic tangent and also the elastoplastic behavior for this typology of devices. And the closest result that we will be able to compare graphically, I mean, this time series. But the I remember that the closest result was the one related to the elastoplastic hysteretic rule, which was something approximately equal to 113. So pretty close to the to what happens here. And this is actually what we were expecting from the software, just because the software actually implements the same behavior. Yeah, then there are also other issues, as we mentioned, that is the actual influence of the applied vertical load fluctuations during motion on the lateral response, and this is generally not modeled when we consider the analytical model of a single degree of freedom oscillator. So this is surely something that will be neglected for simplified models like the one we considered yesterday. But we have also seen that if we consider the the single isolator, and this link element was a corner isolator, so the one which is more susceptible with respect to the fluctuations of the vertical load due to the overturning effect of the inertial forces at all the levels of the building. And let's consider at the horizontal plot function the displacement of the isolation system, so that we are able to see the behavior of actually the force displacement diagram for the single device. So display, you see, okay, no, this is not the force, this is the lateral force, but you see that this is the axial force, because maybe that was the last parameter that we checked on Wednesday. So let's go back to shear. Okay. So these were the graphical results that we discussed about on Wednesday. You see that this is quite different with respect to what we are expecting for the theoretical behavior of curved surface sliders, you see that there are actually deformations, let's say, of these branches with respect to the straight lines that we were expecting. And these are addressed to the variation of vertical load. And this is because mainly because this is the response of the single device, and the single device which is considered here is actually at the corner of the building. So this is the location where we have the maximum influence of the overturning effect induced by the motion of all the floors. But if we go back by analyzing the base shear, and the base shear is actually addressed to the total isolation force. So all all the isolators together, you see that, okay, there is a, as you may remember, there is a minus here for the force for the vertical axis, simply because we are considering the base shear, and the base shear is a reaction force. So there is a minus with respect to the force applied to the isolation system. But nevertheless, we see here that the inclination, the slope of the post-yielding lines is exactly constant as we were expecting from the recentering behavior of such devices. So this means that we can also expect some agreement, a certain agreement between these results and the results that we obtained yesterday for the single degree of freedom oscillators. And because okay, here we just consider the theoretical behavior, and here this is obtained also for the 3D model of the overall structure. Just because this happens, because actually for one location, which was actually this isolator, when we have the motion which causes actually a variation, an increasing value of axial force of compression. At the same time, at the opposite location, we have the decreasing value for the compression. So averagely, the response is actually equal to the theoretical one. But locally, where all the isolators are subjected to variations of vertical loads, and so the main result that we get is actually what we have seen, like in the example for the corner isolator here. So a fluctuating horizontal response as well as the vertical one. So we can also have a look at the other, all the other, hysteretic responses. So let's say, okay, again, base shear. Let's remember that there is a minus in the vertical direction, the vertical axis. For earthquake 2, you see here the maximum displacement is 154 millimeters. Okay, so no, maybe this is sorry, this is the force. This is 200. Yeah, the maximum displacement is 220 millimeters approximately. So we are getting closer to the design value, which was for curved surface sliders was 180 millimeters. If you remember, I just take this spreadsheet, which shows actually the curved surface slider design. We assume the isolation design period as 2.6 seconds. Okay, it was 2.593, so approximately 2.6. The equivalence damping ratio was 30%, and we computed the demand in terms of displacement equal to 180 millimeters. So here we have a displacement demand larger than 200 millimeters. So whereas in the first case, for the first earthquake, we got actually a much lower value for the maximum displacement. Here, this is higher than the design one. So this is what I meant yesterday. So maybe by looking at the results of the single degree of freedom, also here we will see some events which have actually a larger displacement demand with respect to design, and most of them actually they will have a lower value, just because if you remember, the last event has a huge displacement demand, but at the end we have actually the spectrum compatibility, which is checked for the suit that we have adopted. So let's have a look at also earthquake 3. So here the maximum displacement is quite low. You see there is 113 and 77 millimeters respectively for the minimum and the maximum, but generally this is the range of variation for such values. So this is the fourth and so on. So now we have to start by checking all the results. I mean, at least we have to start by collecting results, and then we have to compare them within the MATLAB environment together with the script that we implemented yesterday. So how to save results from sub 2000 in these terms of force displacement? I mean, okay, we are able to, I mean, to compare for sure the base shear with respect to the displacement. So we will actually want to export this data, okay? And actually, in this way, we will get all the information within a single file, because actually we will have the time vector, the displacement vector for the isolation system, and also the isolation force. So also, if we want to consider the time series, just the time series of displacement, in order to compare with the results of the single degree of freedom oscillators, we can do that. We can just because we have all the information in that file. So to do so, we have to open actually the drawing of the force displacement diagram. Let's consider the base shear, so that we can directly compare these series to what is obtained analytically. And so we go to File, you see print tables to file. Okay, so in this way we are able to save a TXT file which contain directly the results for this drawing. So let's go just to the right folder, and here, okay, sub 2000 results. I've just created a folder specifically for that. And we have to pay attention on the name, just to be sure then afterwards for the data processing to select the proper, the proper file. So let's start with the name of the isolation device typology, so CSS, curve surface sliders. And then this is, okay, force displacement loops. And this is for earthquake 1, you see. So earthquake 1, and that's it. If you go to this folder, okay, this is the file, and if you want to see the overall organization of the file, we have a number of other lines, and then we have the description of all the columns. So we have the time vector, the function in terms of joint 4-3, which is actually our reference point for the reinforced concrete plate. In terms of, you see, displacement UX, so the horizontal displacement along the X direction, and then the base shear along the X direction. Okay, and we have all the numerical values. They are according to our you see units, which are summarized here. There is also the software version and so on, and we have all the points. So I think that we can try also to use just not to erase these lines. It strongly depends on the definition of the loading function within MATLAB. Let's try firstly to save all the files and then to check how to compare them. So I just close this file, and then let's keep saving all the information of all the analysis. So okay, then I have to change earthquake 2, and then save it again. So I just click here so that we are keeping the same name, and then I just change the number of the earthquake. Okay, it is a little bit boring, but actually when we have to carry out data processing, obviously we have to do something like this. Okay, 3. Then the 4th. And we will see not only these results, but also other results which can be directly compared to our analytical computations. It takes sometimes a lot of time to compute results, and you will see, especially when we have to consider the base shear at the building location. So you have to we have different strategies for computing the base shear. We will see 2 of them, the most important ones, and actually we one of them is generally also used for experimental purposes when we have to consider shake table tests, which are actually more uncertain with respect to a numerical model. Okay, last quick. Okay, this was the huge displacement seismic event. So this is the 7th. Okay. Okay, then we will be able also to see other results, but at least let's start from these. Okay. Obviously, if you have questions, please ask. Do not hesitate to interrupt me. So I think the curve surface slider was the first version of the script. So let's open this. So what we want to do is the same computations of yesterday. So we will run exactly the same script. And if you remember, we had 2 strategies for the implementation of the force response. The first one was the elastoplastic behavior with hardening, and the hardening is ruled by the recentering behavior. And the second integration method considered the force response as a function of the hyperbolic tangent of velocity, which is actually the force which approximates the sign of the velocity, but with a continuous transition through the 0 velocity value. So if I run these, we obtained the results that we got yesterday. You see, these are the hysteretic loops. And these are for all the events, you see. Okay, and this is what we want to compare according to the results that we got within the SAP environment. So this is the end of the cycle, which considers all the files. So we can try to do it here. We can also try to store the maximum displacement and then to see how much are different one to each other. I mean, sub 2000 with respect to the single degree of freedom assumption. So I think that we can call data equal to, this is a txt file, a text file. So this means that we have to use again import data. Okay, so the name is, this is for CSS devices, so curved surface sliders. So we can just set the, I mean, the string, which is related to the name of the file, which is something like this, CSS, and then force displacement, and then earthquake. And then we want to actually to increase stepwise the name of the earthquake in order to compare then all the files. So we have mat to string of the index related to the file, and then finally we have the extension of the file, which is .txt. Okay. This is not enough because import data with no other input values perfectly works only whenever you have txt files with no header. So since we have header, we have to go back to the definition of the files. We have to count actually the lines for the header, which are 15. And then we can also try to the limiter, to set the limiter. So I think that if we go to the help import data, you see that there is the first information is the delimiter, and then the number of header lines. Okay, so as delimiter, let's set tab, and then we set 15 lines of header. So maybe it is just a number, not a string. Let's try. Yeah, you see, unable to open file. So let's try to do this. Otherwise, the easiest, because the easiest thing is just to erase the header lines. So if we go back to the help, there was, so maybe the space. No. And so the delimiter, let's see which can be the delimiter. Yeah, this was tab, or maybe space. So this didn't work, and so let's try this space. Okay, so the easiest is just to use import data and then to erase in this way. Okay. So in this way, it is better. So every time I try to remember how to do this, because one time I think at just once I was successful in using import data by setting the header and the limiter, but every time I forgot how I forget how to do this. So okay, save. Let's close it. So now it should work. Let's type a return just to stop, because then we have to do something like this. So maybe it was right, because now I have understood what it was wrong. It is actually at sub 2000 results, you see. So maybe this is the main reason. Okay. Okay, so now it works, obviously. Then we will try for lateral bearings if it works also with the header. Then we have the time sub equal to data first column. Then we have the displacement for sub, which is data second column. And then the force of sub 2000 is data third column. So let's set here figure 1 so that we are sure that we are just considering that figure. There is already all done before, so we can just type plot the sub with respect to minus f sub. Minus because if you remember, we have just saved the base shear, and the base shear is just a reaction force, so there is a minus. Okay, let's consider just once. Return. Okay, so let's also add a legend just to be consistent, and then also the grid. Then also the name of the label. And finally, the Y label. Okay, and then the legend. We have 3 plots. This is sub 2000. This is the hyperbolic tangent, and this is elastoplastic with the hardening, let's say. Okay, I just want to make all the plots a little bit thicker. So I just want to set the line width set to 1.5 is enough. Also for the others, so that it's better. Okay, so this is the total set of results. The comparison between both the first and the second are actually analytic models, and then the yellow one is related to sub 2000. So you see that according to the maximum displacement, we have a very close, which is this one at this location. We have the maximum deformation. So we have actually the closest results, which is related to the elastoplastic behavior with hardening, you see. And the overall response is fairly represented also by the single degree of freedom oscillators. We have exactly the same force response and the same global behavior. Let's say we have different branches, but actually this is related to just related to the hysteretic response. I just want you to have a look also at the displacement time series. So let's try to consider these. So we want also to change the number of figures accordingly to the number of the earthquake. So we will have two figures, the one which shows the hysteretic response, like this, and then the hysteretic response, and then the displacement response. So twice di file minus 1 will be the index of the figure for the the force displacement loops, and then we will have a figure just twice the I value for the file. This is okay. I just copy these because we have just to change the typology of the drawing. Okay, so T comma and T comma. Yeah, now if you see, I've just defined T sub 2000 as the first column of the imported file, but actually the time vector is exactly the same between MATLAB and sub 2000, just because we have assumed the time step for results, which is exactly equal to the time step for the MATLAB and generally for the input. So I just see that maybe there will be just a difference for the total length, because maybe for SAP you see that there is an additional value which is computed. So that is the only difference. It is better to separate the two because the additional point is obviously at the end of the results. So then we will also copy and paste these. And here we have to change to T sub 2000, and then that's it. So here this becomes dy, and this dx, and this will be time. But this is twice I file. Okay, let's start. Okay, so this is the comparison for the time series. Okay, you see that we get very close for the peak response. Then there is a certain mismatching, actually, even though the trend is fairly captured by single degrees of freedom oscillators. And actually, we have these additional behaviors, because obviously in sub 2000 we have also the behavior and the response of the building. And as I mentioned in previous lectures, you see how the elastic response of the building leads to a lower value of residual displacement with respect to all the other cases, which are just related to single degrees of freedom, where there is just the recentering behavior ruled by the restoring stiffness. And this is what I meant, actually. The elastic response of the building leads to an additional contribution for the recentering capability of the isolation system. So you see that even though we have approximately the same behavior, and we achieve approximately the same displacement here, and then there are some additional fluctuations of the superstructure, which leads the overall system to displace back to the zero configuration. Okay, so this is not always true, but at least in this case, this is what happens. And this is general average what happens also for other, we are expecting to find exactly the same behavior also for the other earthquakes. Let's check. So I think that we can directly, yeah, we could also try to check the force time series, but then we will do it later. So let's do it for all the earthquakes. Okay. Okay, something here. I don't know why this doesn't work. Why? So there is no second column for and data. Okay, so there is, so maybe there is a file which has not been modified. No, that is quite strange. Okay. So the file is this one. Okay, so maybe it is in the fourth. Okay, yeah, there is just a single header line. Okay. So now it should work. It takes a bit of time, but actually it has to consider all the earthquakes. So this is the seventh earthquake. This is in terms of time series of displacements. You see how it is actually well captured also by the by the single degrees of freedom. We have approximately the same response. For maximum values, we are very close. Also for the minimum. And then for the residual displacement, you see that, okay, we get close to zero, but you see what I meant yesterday, according to the hyperbolic tangent. You see that the hyperbolic tangent is generally associated to zero frictional force when we have zero velocity. So what we have is actually a continuous and continuously applied restoring force to the device and generally to the system, with no frictional resistance. So what we get is this branch, this red branch, which goes slightly and very smoothly to 0. Okay, and this is not what happens when we instead we model the frictional response according to the elastoplastic behavior. You see that once we get close to the final value of displacement, it is kept constant along the final duration of the earthquake. And these results are pretty close with respect to the comparison between the single degree of freedom and the sub 2000 model. So this earthquake, which is the strongest one, I mean, the largest event that we considered within our selection, actually can be modeled with the same accuracy, also with a very simplified method, which is the single degree of freedom analysis. Let's have a look at also the hysteretic response. And you see that this can be seen also from these graphical results. And you see here the hysteresis loops for sub 2000 and the elastoplastics look like approximately the same. There is a little bit of variation related to, for the peak, I mean, for the peak value related to the elastoplastic, in single degree of freedom. And here we have this decreasing value which goes towards 0, which is actually the one related to the hyperbolic tangent, what we have observed also from the displacement time series point of view. So let's go to have a look also to other earthquakes. This is the 6th, so it is better also to set some title just to see the correct earthquake. Okay. And then we consider this also for this. Okay. So we are able to check the proper number of the earthquake. So we have already seen the 7th earthquake. And now we can start by analyzing the 6th. Okay, now the sub 2000 model leads to a higher value of displacement, as you see. Then we have a fairly good representation of residual displacement, but according to the peak displacement, we are underestimating the lateral displacement with a single degree of freedom. And this is mainly due to the additional contribution of the overall superstructure, which can actually lead to higher displacement sometimes. And the same can be seen also from the hysteretic response point of view. You see that the sub 2000 hysteresis goes much beyond the peak the peak displacement that has been obtained from the single degree of freedom oscillators. And then we can find the maximum variations between the two approaches. I mean, for single degree of freedom and sub 2000, so the full 3D model, as soon as the overall seismic event leads to a lower value of the displacement. So here, for instance, we have a very good agreement for the peak value, which is negative. Actually, we have approximately the same value, with some additional differences in the opposite direction, the peak value in the opposite direction. And then we have, if we consider the absolute value of the residual displacement, they are the same, but actually they are in opposite directions. So you see that how here in this at this time instant, the influence of the motion of the superstructure of the building leads to the overall system to the opposite direction here with respect to the single degree of freedom assumption, which remains mainly in the positive values of the displacement. So this can actually affect the overall response, but you see that generally the peak value can be fairly captured also by simplified models. And the same, you see now how the in the peak, the very maximum displacement, which is negative for this earthquake, which is the fifth, how the two hystereses are approximately overlapped with the same assumptions. I mean, because we have computed the initial stiffness according to the same value of the rigid. If you remember, we assumed 1.5 millimeters to develop the frictional force, and obviously the same friction coefficient, which was returned by design. And okay, this is earthquake 4. The peak value is here. There is actually a certain difference here, and there is a difference also in the opposite direction, but this is not the peak value. And these are obviously addressed to the influence of the superstructure. But here there is also a very good agreement between the final lateral residual displacement. There is a mismatch, an additional mismatch with respect to the previous cases, according to elastoplastic history with hardening for the single degree of freedom and the sub 2000 modeling. So this is mainly because of what we discussed about yesterday and also today. So generally the superstructure, the elastic response of the building, of the frame structure, I mean, leads to lower values of residual displacement, and this can be detected actually according to all the earthquakes.
Professor, sorry, one question.
Yes.
Can you explain again why the maximum displacement tend to be higher for the SAP model?
Yeah, generally because of, also for the maximum displacement, this difference can be addressed as well to the overall response of the frame, because the frame tries also to actually to lead the overall system to higher displacement, displacements. I mean, so I think that the only difference here is that okay, in sub 2000 we have a three-dimensional model. We have the proper flexibility or stiffness, let's say, for the frame structure, and so automatically these leads to discrepancies with a very simplified model, which is actually the single degree of freedom oscillator. We just consider a rigid mass over the whole isolation set, and the isolation system is considered as an equivalent isolator, so just with the 1 degree of freedom. So all these differences leads to higher values of displacement generally within the finite element model with respect to the single degree of freedom oscillator.
And that difference is bigger for more flexible structures.
Yeah, exactly. Because as soon as you consider rigid, more rigid structures, you get close to the assumption of a single degree of freedom oscillator. So as the self period of the fixed base configuration of the building increases. So if the period increases, this means that the overall flexibility increases, so the stiffness decreases. We can say it in both the cases. And so that we are expecting some additional discrepancies between the two strategies. I mean, but actually, if you consider an infinitely rigid structure, actually you are very close to what happens to when you consider just a single degree of freedom.
Thank you. Perfect.
You're welcome. And so finally, okay, just have a look at also the first earthquakes. You see here we have, if we want just to erase the one related to the hyperbolic tangent, let's check. So this is the comparison with the models sub 2000 and the single degree of freedom by assuming the same hysteretic behavior. So you see that they are averagely overlapped, averagely for the whole duration. There are some discrepancies, but the the peak value is approximately the same. And this is what we are interested in computing now, the analysis of the peak displacement, because actually we have to consider that to check actually the efficiency of the designed isolation system. So the same results for here, for the hysteresis and the overall response. This is a good agreement for earthquake 2. Also from the force displacement hysteresis, and this is what we already discussed. Earthquake 1. Okay, so let's try to consider differences in the numerical values for the peak quantities. So I want to consider both the displacements and the lateral force. So the displacement here is already stored for the single degree of freedom. We have to actually to store the maximum force also for the single degree of freedom. So maximum value of absolute value of F isolation. Let's consider the F isolation for the elastoplastic behavior, which is the first, okay? Which is actually the closest which can be considered for the, but we can do both. There is no problem. Okay, so F max 2, and we consider F isolation 2. Okay, so that we are able to compare all of them. And also let's do it also for here, for the maximum displacement. So the maximum 2 and U2. Okay. And then we have to do it also for sub 2000. So the maximum SAP equal to, okay, this is for the height file, equal to maximum of absolute value of, it was the SAP. Okay. And then we have F maximum SAP, which is the same. Okay. So finally, we want a bar plot. So let's check both together in the single figure. So we do a subplot, 1 row and 2 columns. And in the first, we will consider the bar plot among the earthquakes. And we will consider the total set of the displacement. So the maximum 1, right? No, the maximum, just the max. Okay, then the max 2 and the max SAP. Okay, so and then that's it. Okay. We have earthquake. Okay, and this is maximum displacement. And then the same for the second subplot. So this. So here we have just to change to F. This is F and this is F. Maximum force in kilonewton. So let's see what happens. Okay, generally it is like this. So let's check what happens if I compute this. So the answer is 3 by 7. So why it doesn't work? So maybe because we have to transpose. Yeah, we just needed the transpose. So okay, we can do these and do these. Okay. So these are results for, okay, at the left, maximum displacement, and at the right, the maximum force. You see how much they are very similar one to each other, and especially not always. I see that I was expecting to find the elastoplastic with hardening for the single degree of freedom much closer to the response of sub 2000. But you see that it is not always true. In the first earthquake, for instance, it is true. Also in the second, but in the third, we are overestimating with the elastoplastic behavior with respect to the hyperbolic tangent. And okay, in earthquake 4, both of the single degree of freedom models underestimate the response in terms of displacement with respect to sub 2000. Okay, earthquake 5 effectively has the good agreement between the elastoplastic behaviors, the finite element model, and the single degree of freedom. Also, let's say for the last 2 earthquakes. Generally, the variations that you can find in displacement response are generally higher with respect to the variation that you can find for maximum force. And you see that here we have approximately the same drawing, but the numerical values are much higher. So this means that generally the variations are lower, much lower for the force. So I think that this is it for the curve surface slider, and we go. I think we can just also check another very important quantity, which is the mean for all this set. So I think that this is the answer is 3 by 7. So we have to compute the mean. Okay, so I think that we can do these. Okay, 8 and 8. Let's try if it works. Okay, so we need the mean of these. And with respect to columns, okay, and then transpose. Let's see if it works, because I want to see also the the average value for both displacement and forces, because actually the average displacement has to be checked according to the design value. So let's check if okay, we have some variations with respect to the with respect to the single event response, but maybe we get closer, much closer, if we consider the average values. So let's check if it is the case. Okay, so the 8th, just to be consistent, I just want the last tick to be called actually mean. So so this is mean, and then we have 1, 2, 3, 4, 5, 6, 7. And these also for the previous. Then the legend, maybe it is better to move it at the left, which is the west, north, west. Okay, and that's it. This is just to get some invalid. Yes, GCA, get current axis. Okay. Okay, so this is just for fancy results. I mean, you see, now we have the single events and then the mean. You see how mean values are approximately the same for both displacement and force. So, okay, we have some discrepancies for the single event response, but then at the end we have exactly this, approximately the same value for all these strategies. And let's check also the numerical values. So I just highlight that the design displacement here was 180 millimeters, so 0.18, which is this one, and we are approximately at the same magnitude order. So I think that this is fair enough to say that the overall design isolation system can actually work for the case study structure which has been designed. Okay, so if there is no question about this, we can just move to the analysis of the results for the lead rubber bearings. So let's close this and let's go to the model. Okay, let's save and let's open the model for the rubber bearing, lead rubber bearings. So I can close it. So I can close also here and clear. Okay, then we will try to get exactly the same figures. So we will just copy and paste the definition from here, I think, to the last, because for lead rubber bearings we had just a single, just one strategy because we have elastoplastic behavior. So now we have to store results and to see, okay, base shear with respect to the displacement. And so I just want you to see the maximum displacement event. So you see, this is the overall behavior that we already observed also for earthquake 1, and this is also implemented for all the other earthquakes. So let's try to save again all the numerical files. So print file, LRB, force displacement, earthquake 1. Okay, then earthquake 2. Earthquake 3. Then you see that we achieved the convergence very easily. So half an hour to run all the analysis, and with no, no mistakes in the, no strange behaviors within the solution. So this is good according to what we found. This is a very small displacement. This is a bit strange. No, yeah, this is because the fourth was that event that we started, and then maybe this is because it is not finished here. This is a very starting point. Okay, so we have to run it again. Just a second. Okay, so it will run very, very fastly. So this is the fifth. Okay. The sixth. And the seventh. The largest one. Okay. Okay. Done. So if I want to run the fifth, okay, I hope. Yes. Okay, so run. Okay, everything else is finished. Okay, so run. I was just missing the fourth because we, if you remember, we interrupted yesterday the analysis at the fourth earthquake. And so maybe when I started all the analysis this morning, this earthquake was not considered as a missing because as a missing earthquake, just because there was some results just for the very initial time instance. So we have just to wait a little bit. So you see that we have convergence at every time step. And this is another information of the good convergence is also that sub 2000 doesn't change the time step size. We know that the implemented time integration method within sub 2000 changes actually the time step size according to the overall numerical instability and in order to better achieve convergence at each time step. So if we check that the the type step remains always the same, this means that it is the convergence is easily achieved for the whole duration of the earthquake. And this is obviously something good. This means that the overall mechanical properties have been defined with, it is not bad conditioned or ill conditioned, and there are the overall mechanical properties which are fairly good for the proper representation of the behavior. So you see that the elapsed time is just 2 minutes, and we are almost done. Okay. Then we have just to save the graphical results for earthquake 4, and then we go to analyze the overall results in comparison to the single degree of freedom. Okay, so completed. It should close. Okay. So yes, a warning, just because we have the initial value of the accelerogram, which is different than 0, but that is not a problem for us. So earthquake 4, display. Okay. Print table to file. Okay. So now we have all the results for the rubber bearings, for the lead rubber bearings. We go back to MATLAB. And okay, let's copy and paste, I think, all this stuff. Okay, and then let's open the, I think the second one, lead rubber bearings, yes. Okay, so this, okay, perfect. So here we don't have these, we don't have these, we don't have these. Okay, we have just a single strategy for the single degree of freedom. And okay, so here I just have to forget about these and also these. So here and here. Okay, and then we don't have. Okay, perfect. Also here we have elastoplastic with hardening. Now it should work, but okay, we have to change the import data. But now I want to, I do want to consider the tab because maybe the previous mistake was because it was missing the name of the folder. Maybe. Let's try tab and then 15. This is just a trial. Where is? This end is useless. Okay. Okay, so data. Okay, it is not the tab, maybe. So maybe we have the space. I think that maybe we have the structure, data. But this is data, correct? Okay, let's say, yeah. So these are 16, so it is good. So maybe if I just set here data equal to data dot data. Okay, we did it, but there was an additional, I mean, legend. Let's erase it here. Okay, and also here. Okay, now it should work better. I don't like to see errors here in the command window when I run MATLAB, so if it is possible, even though they are warning. So these are results for displacement and maximum force comparison. And we were actually modeling, okay, there is a certain difference, but maybe, okay, for the displacement, that is actually the proper difference that we have according to the overall response. And we can see that there is no a given trend. I mean, it is not always true that the single degree of freedom has a lower value of displacement, but for instance, here it is higher, here is lower, so it strongly depends on the, I mean, the overall definition of the seismic event. Okay, here we have also some discrepancies in the force response, but maybe I don't remember how we defined yesterday the force response of the whole system. Maybe we have also to sum up the contribution of the flat slider, you see. So if I just take the maximum force of the isolation, these are just forces related to the isolation devices, so the lead rubber bearings. I just need also to check to sum up these contribution, because otherwise we are missing the flat slider response just for the single degree of freedom. I mean, because in MATLAB, I mean, in SAP 2000, we already have that contribution because we have the base shear, the total base shear. So plus force flat slider, and that's it. Just run. Yeah, and maybe the time series. No, okay, maybe. Okay, you see that. Okay, now results are updated and they should be they should be right. In this way, we are considering both the responses related to isolators and related to flat sliders, which is more, actually a result more comprehensive. But maybe by looking, okay, this is the comparison for earthquake 7 of the displacement time series. It is a fairly good comparison. And this is for the hysteretic response. You see that there is this difference, but this is because for sure we are missing for the elastoplastic also the contribution of the flat sliders. So let's have a look at that. I mean, we have to go back to yeah, you see there is a little bit difference between the two, but there is a difference actually for those I mean for the force response. So let's go back to check if everything is set in the proper way. So when this is the hysteresis plus the force flat slider. Okay, perfect. And the force for the flat slider, okay, is updated here. Okay, let's run again. Okay, so we have these differences again. Okay, we have again these difference. And okay, here there is this additional difference, and actually there is some difference with respect to the elastoplastic, and this is directly related to you see the thickness of the hysteresis, and I mean, if we account for also for flat slider, the difference, since the single degree of freedom response is higher, the difference will be much higher. So this can be addressed to the flat slider response, just because of these in the single degree of freedom oscillator, we accounted for the average vertical load, and this means that we are maybe underestimating the I mean the overall response directly associated to the friction. Okay, because actually for lateral bearings we have just 4 bearings, 4 isolators at the corners, and the remaining supporting points are represented by flat sliders. So this means that we have the internal points of the structure, which are represented by flat sliders, and these are the actually the points where we have the maximum value of I mean vertical reaction, because we have actually the internal points, so we have the largest amount of external loads which is applied to all the floors. So maybe to consider the I mean the average vertical reaction is not the best solution for comparison. So what we can do is just to analyze the numerical values of all the reactions for the points where we want to install flat sliders, and this can be done without carry out the nonlinear time history analysis, but at least we can consider the gravity application at the very last time step. So let's check internal forces for joints, and we want to consider gravity at the 15th seconds. Okay, let's see. Okay, these are values, and I want just to forget about everything and just to see values. So I just want to select frames, so both columns and also the plate. So properties, area section, the plate, select, and this is show remove selection from view. Okay, perfect. So let me go into the direct text, which is much. Okay. So you see that we have, okay, here we have 455, and actually for the single degree of freedom, we considered this summation, which is actually the 10,000, something like that, 10,000 kilonewtons. So that should be a little bit higher, because we have just the total amount of the total weight minus the 4 reactions which are applied to the devices, which are the corner, so the 315. So we can try to do this just to check if we can get some better results. So This is the average. So we can just define the average. So the summation of everything for the flat sliders as the total weight. So this is flat slider equal to the total weight minus 4 times the single reaction of the isolators, which was 315 kilonewtons. Okay. And so let's try to check if results get closer. Okay, this will deal with just the force response. Okay, I think that they are a little bit closer than before, but then we will check the hysteresis. No, you see that averagely we have the same behavior. So I think that maybe there is we have just to check the number of isolation devices, which is 4. Okay, so I think that this is good. So generally, these are differences which can be found, but I think it's too much for this isolation.
I'm sorry, Professor. Can I ask you?
Yes, sure.
I'm not sure we are loading the correct file from SAP 2000 in the MATLAB environment.
You are perfectly right, because I didn't change the lead rubber bearing. Perfect. Thank you very much, LRB. This is right. Okay, so let's try to check. Okay. Okay, so now it's even better. Let's check. Okay, the displacement. Okay, so now everything looks like how it works. So let's try to go back to the previous definition also with respect to the average flat slider reaction force. So maybe, okay, the last one that we have computed is the best computation because it is actually the summation of all the reaction forces for flat sliders. But generally, I just want you to see how much is actually effective the simplified model with the single degree of freedom. So just very briefly to compute the average total weight applied to the flat sliders. Let's see if we look at some differences again. Okay. So you see that there is a little bit difference, you see, but they are actually very limited. So it is better to use the second one if we are able to perform, to perform just a gravity load application. And but just if you want to consider the response, the lateral response of the isolated structure, and you don't have to build the finite element model, you can just compute also the average total value of friction, of gravity loads applied to flat sliders, and you see that you come up with a fairly good estimation of displacements. And also for residual displacements here, you see SAP 2000 goes back to 0 because there is the influence of the superstructure. So here, yeah, we are pretty closer to 0, but here values are very limited. I didn't check. Okay, here there are some differences, you see, but just because there is some low value of displacement, I didn't check the peak values of displacement. I want to go back to have a look at that. Also for the mean value. Yeah. Okay, so we have a number also for lead rubber bearings. We have a number of variations, but finally, you see we have approximately the same mean value. And the numerical value is something like 173 approximately. Yeah. and 72 for sub 2000, which is lower than 180, which was again the same value for also for lead rubber bearings in comparison to curved surface slider, because we had the same period value and the same equivalent damping ratio. And I think that this is good. So finally, let's consider the response of rubber bearings. So let's open also rubber bearings model, and we need to go actually in the rubber bearing. Okay, file. Oh, maybe now I have opened the student version of the program, so I have to open it again. But you see, what I wanted you to see with these numerical laboratories is that actually is able for us to perform some easy computations with the single degree of freedom oscillators, which actually gives a fairly good estimation of the displacement and force demand of the isolation layer. And so we are able to check if the mechanical properties that we have designed are actually good for the displacement demand that we obtained. Okay. So without computing any vertical response, so also without computing the gravity load application, we can get to very close results in terms of the horizontal response. So both the hysteresis and the hysteretic response, and then the displacement time series. So this is the rubber bearing model, and I don't know why it is unlocked. This may be maybe because I've just opened with the student version of the program, so maybe I need to run again the analysis. This is bad. Okay, so let's try to run everything. I think that we will just need a very limited time. So according to these, we can also try to check within the lead rubber bearings and also for the curved surface slider what we didn't see before for all the for all the events, which is actually the hysteresis loop directly associated to design, which is actually one request that is listed within the final homework that I've just sent to you yesterday. So obviously you're not asked to run analysis through sub 2000 rather than simulations with a single degree of freedom, but you are just asked to provide the drawing of the force displacement loops of the single device according to design, and also of the whole isolation system. So it means that whenever you have rubber bearings or lead rubber bearings, we for the total system, we have to sum up what we are expecting for the response of flat sliders and the total force associated to isolators. So for instance, if we go back to the curved surface sliders, okay, this is the easiest case where we have the all the isolators located at the supporting points. We can just build the overall drawing. We start from displacements meters, and then force in kilonewtons. Okay, here is it running? Yeah. Okay, so 27%, so we are almost done. Then we start from 0. Then the okay, this is just a theoretical hysteresis loop. So this is the not the single device, but let's consider the total isolation system. Okay, so the then afterwards we have the maximum force, which is the actually the weight mass times 9.81, so the gravity acceleration times the the design value of friction coefficient. Okay. Then we have the friction coefficient, I mean the frictional force plus the recentering contribution. So we have the weight times 9.81 divided by the equivalent radius of curvature times the displacement. Okay. Then we have that force minus twice the frictional force. And then we have these minus the weight times 9.81 divided by R equivalent times 2 times displacement. And we should get exactly that. The maximum value is with a negative sign. Then this plus the frictional force, and then back twice the frictional force. Okay, and then back to the frictional force. Okay, so here we have, so these are forces. I don't know why I listed it. I listed them within the displacement. So the displacement were 0, 0, maximum displacement, negative maximum displacement, negative maximum displacement, and 0. So just looking, this is just by considering points. So you see, this is the hysteresis which is assumed in design. So a fully symmetric, a fully reverse cycle at maximum displacement, so which is actually the design one, and then the friction coefficient that we computed in design, so 5%, and then the restoring stiffness according to the equivalent radius of curvature that we computed. Okay. So here, just to get the single isolator response, we can just divide. We can compute as an average one, so we can just divide the total isolation system by the number of the supporting points, since curved surface ladder are installed within all the supporting points. And then you can do these also for the lead rubber bearings and the rubber bearings. I mean, for rubber bearings with and without the lead core, I think that the best case, the best solution is to do exactly the computation continuously. So what we, similarly to what we modeled yesterday, with the sinusoidal waveform for displacement, and then with the hysteresis rules that we computed for the single degree of freedom, but not for time integration, but just for representation of loops. Just the curved surface ladders can be just simplified like this. I mean, it is very simple. So let's check back these. Okay, it goes. So if you remember, yesterday we considered these, which was actually the example for CSS, and this can be done also for it can be used actually for the definition of the hysteresis of both the isolation and the single device. Just because here you can set the design value of displacement, here the friction coefficient, the total weight. You just need to add the equivalent radius of curvature. So if you add it here in terms of meters, 3.16, and then we can just add plus the weight times divided by the radius times the displacement, and then we have just to fix some reference. Okay, so you see we get exactly the same. So here we have the proper definition of maximum displacement. So this was approximately the right value of the weight, regardless of the value of the frequency and of the maximum velocity. This doesn't actually provide any influence to the final result that we want. Okay, so also for the second. Okay, so if you just compare the maximum force here, we got 1369, and this looks like the same here. So if we want to compute the maximum of these, yeah, a little bit different, but I think that maybe there is some difference here. Yeah, so if we just copy and paste, so you see that it gets closer. So also here we have differences, also the friction coefficient, but nevertheless, this is a fairly good result, I mean. So we can do the same for also the lead rubber bearings and the rubber bearings, just by providing the two responses, the one related to frictional flat sliders and the one related to either rubber bearings or lead rubber bearings, because the hysteretic loops for elastoplastic with hardening behaviors can be easily implemented within the Excel spreadsheet. So you can do this very easily. So I think it's almost done, and then I'm sorry for that, because I have double clicked on the file, and now the SDB extension of the file, which is the extension for sub 2000 files, is associated to the student version. And once you open the model with the student version, the results are deleted, and this is actually what happened. So up to now, is there any question? In the meantime, we wait for the analysis to end. So generally, for also not only for what we have seen up to now for the comparison of results, but I think since we are approaching the end of this lecture, which is also the end of the short course, is there anything which needs a further explanation or some doubts? Okay, so I think this is good that you fairly understood everything. So I think that we are almost done. So we can just try to start considering the new. I mean, there was maybe two modeling of the flat sliders. So let's go back to see. So here, that's comparison. So the third, okay. No, just one. So we implemented just this one. Okay, perfect. So here we want to consider all this stuff. And here. Okay. Now I know from my mistakes, I have to change the name. Okay, we don't have the file, but at least we are going to have them in a couple of minutes. And I think we don't have to modify anything else, simply because we have already the definition of everything. Yeah, let's keep the same weight applied to the flat sliders. So the same comparison, we have seen that okay, it is better the comparison if we consider the proper summation of all the reaction forces, but in the case we want just to perform fast computations with no finite element models, we can just compute this average estimation. I mean, so we have 8 devices and so on. So yeah, it takes a little bit for the last earthquakes because maybe we have Yeah, and this is an issue that we didn't apply, but this is very important. Whenever you will have ground motions with duration up to 80 seconds, this is better to be cut, just because we are considering a lot of zero paths. So these zero values for ground motion, which are actually useless. I mean, they could be useful at the end of the seismic event if we want to consider and to study some free vibrations at the end. So it is the same reasoning of considering the initial conditions for the building different than zero, and then to check damped and free vibrations, so without any seismic event applied at the base. But when your attention is not focused on the overall behavior of free vibrations, this is useless, because the ground motion maybe lasts, I think, 30 to 40 seconds maximum. So this is just wasting of time, but at least we assume the same signal that was returned by the Rexel software. So I think that we are almost approaching to finish.
Professor, can I ask you a question?
Yes.
I don't know if we talked about this in the course, but I'm a little concerned. I want to know about maintenance of, for example, lead rubber bearings, and also after a ground motion, a major event, is it by code necessary to check the isolator some way, have some inspection, or what is it done in these cases?
Yeah, it is a very good question. Thank you. This is a very key issue regarding standard codes and generally the maintenance for the isolation devices. I think the biggest issue is related to frictional devices, because actually, if there is dust rather than debris, some debris on the sliding surfaces, you may have some some discrepancies with respect to the real performance of the isolators, because maybe you have designed for a given friction coefficient, but the dust and let's say general debris on the isolation devices can lead to a much higher value. So what you can get is actually that your device has a very large friction coefficient, which means that generally it works exactly like a fixed base configuration. So you have designed isolators, but actually at the end of the day, your building is fixed, and so you get a much higher, much higher damage. And there are some rules for maintenance, also for rubber bearings. At the end, and lead rubber bearings. Generally, you are supposed to check isolators at the end of a seismic event, especially for those devices which have the highly nonlinear behavior, because, for instance, for curved surface sliders, there could be some additional residual displacements, as we have seen. So if they are large, they have to be stored back to the zero deformation location. Otherwise, if there is another earthquake afterwards, so an aftershock which occur, the starting point will not be as the zero displacement, but it will be at a given offset. And this means that the displacement capacity along one direction maybe is higher, but along the opposite is shorter. So maybe your device is not able to accommodate displacements in one direction. And for curved surface sliders, it's quite easy to restore the system, just because it is a sliding. It is a sliding working principle. But for lead rubber bearing, yeah, it is always it is always easy to apply forces with jacks, with hydraulic jacks to displace the building. But actually, for lead rubber bearings, for instance, which have a huge a huge hysteresis, a huge nonlinear behavior. Actually, that should be a plastic deformation of the lead core. So it is quite it is a different situation, and that could be difficult to be restored in a in a zero displacement location, just because that the residual displacement is not just a displacement achieved during the sliding motion, for instance, for the cursor of a slider, but it is a permanent plastic deformation of the material itself of the lead core. So that could be extremely. Maybe we have to replace and to substitute some devices if there is a huge residual displacement. That is, that is a very important issue, and this is mainly because the reason why the standard code try to rule the effective restoring capability of isolation devices, just to try to avoid all these issues at the end of a seismic event.
I see, thank you. Do you know if there's any reference for the maximum allowable residual displacement after an event for the isolator to keep, for it not to require some recentering or replacement? Is there something on that?
Well, I actually don't know if there is on the standard code a numerical value. A prescription, a clear prescription of the maximum allowance of the residual displacement. So I think that it is the structural engineer that has to be who has to actually say if that value is small enough to just not to recenter all the buildings which have been displaced.
I see, perfect, thank you.
Yeah, you're welcome. Yeah, generally standard codes when there are no rules, specific rules, and the quantitative values, regarding some parameters, they just say that the structural engineer has to define them. So maybe it is just upon the decision of the structural engineer. And so we have seen that also the superstructures in a certain way plays a very good role within the recentering capability. And so maybe we get close to zero in all cases, but it is the higher the nonlinearity of the system, the higher could be the residual displacement at the end of a seismic event. So we still need to always to check the and a linear addition of contribution which actually provides the recentering behavior. So as you see, for all the typologies, the recentering capability of the isolation systems is always provided by a linear contribution. For rubber bearings, okay, they are linear springs approximately. There is hysteresis, a very small one, but they are approximately linear. And these are maybe the isolators with the highest contribution with respect to the recentering behavior, just because they are linear. And for lead rubber bearings, the recentering behavior, even if it is very small, it is provided by the rubber compound exactly as well as the rubber bearing. And it is actually modeled as a linear behavior. And also for the cursor of sliders, the spherical shapes of the sliding surfaces just leads to a stepwise projection of the applied vertical load, which is modeled through a linear function. So whenever we are able to apply something linear and to add something linear, that is an additional, useful contribution for the recentering behavior. That could be also an external device. If we are not able to install isolation devices which have already some capacity for the restoring capability, we can just install something like a damper, an additional damper or a spring, which provides the the proper linear behavior, which leads to a lower value for the final residual displacements. I mean, that could be another strategy.
It's clear. Thank you. Can I ask you one more question? Sorry for
yes.
that many questions.
No, yes.
In lead rover bearings, I'm sure that the rover has some strain hardening behavior, maybe at high strains.
Yes.
Is this behavior important? Or, I mean, we saw that the bilinear modeling probably it's enough, but should it be considered, or should we think about it, or is it just not influential in the design?
Well, that is a very good, a very good question, because we can get some sort of additional hardening when we go through very high values of the lateral shear strain for lateral bearings. I mean, for the evaluation of for a very fast evaluation of the displacement demand, this could be actually neglected at the beginning, but this is a very good, contribution for the isolation devices for if it is considered and actually modeled for very severe earthquakes. So maybe we have actually the ordinary response for the design earthquake, but then if there is an earthquake which occurs, which is very severe and very strong, the additional hardening when we have a larger value of lateral shear strain provides a sort of additional strength for the overall isolation system, which tries to limit displacements, even though the intensity of the seismic event is increasing. So that is something which has to be accounted for. Depending on the level of detail that we want to achieve. So if you want just to perform some very fast computation, you can just consider an elastoplastic with the hardening related to the rubber compound. But then there are a number of nonlinear links, for instance, also in OpenSeas, which can directly model this hardening effect, also due to the, shear straining, so the actually the high shear straining.
It's very clear. Thank you. Thanks a lot.
You're welcome. So very briefly, I just want you to see also results for the rubber bearings, and so I just go fast. So base shear and so on. Okay, so here we have the influence of both the flat slider and the hysteresis provided by the equivalent viscous damping. Okay, let's change here rubber bearing. Okay, earthquake 2. Earthquake 3. Four. Okay, 5, 6. And 7. Okay. Save. And that's it. So here we should be ready to perform. Okay, we have a rubber bearing. Let's try. Extra legends. So maybe there is I don't know. So how can we get the final displacement and then maybe so let's close everything. Okay, it works. Okay, let's run it again. I don't know why this happens. It worked for everything. Now it has to for the single event. So we have F isolation. Then we have also to add the flat slider. Okay, so this is the case. Okay. Then we have the okay. That should be exactly the same for the as exactly as before. So maybe we are okay. So there was missing the plot. This one, yeah, this one we're missing. Okay, let's do it here. Okay. Okay, so now everything works. So you see that here results are pretty close to sub 2000 with respect to the single degree of freedom, just because rubber bearings are linear. We have a very small amount of damping, even though we are implementing also flat sliders, but generally we are expecting a better behavior for rubber bearings. So you see how they are overlapped approximately all the signals for the displacement, and also by looking at hysteresis, there is a little bit of a difference, but generally we have the same, the overall behavior, which is fairly represented by also the single degree of freedom. Same for all the earthquakes. You see, and generally, this is the most linear. I mean, the most linear device that we can get for isolation purposes. And one characteristic, as you can see by looking at the time series of displacement, is that there could be also a large number of harmonic waveforms. You see, at large displacement. Here we can have 2.5, let's say, because the last one has a very limited value of maximum displacement. And this doesn't happen for non-linear devices because you have seen that for CSS and lateral ball bearings, we don't have actually many harmonic shapes and many subsequent cycles. I mean, but we have maybe just a single harmonic wave. And this is something which is currently discussed for the revision of the standard code for testing, because maybe also for curved surface sliders there are tests, as we have seen in the testing protocol, and also in the first numerical laboratory, related to 3 number of cycles, and generally the number of harmonic waves that you can get from nonlinear time history analysis is just maybe 1 and 1.5. So they are surely different than 3. And if you remember, there is also the repeated cyclic test, which is 10 cycles. So something very different than what you can find generally with nonlinear time history analysis, which should be something very close to what happens in reality. But whenever you have a linear device, so something like a rubber bearing, okay, you see that here there is this thickness, which is addressed to the frictional behavior, but then nonetheless, we have approximately the same behavior for also for the single degree of freedom, and we have a number of harmonic waves also for all the earthquakes. Okay, they could be to various value of displacement, but actually it is a continuously applied frequency, I mean, to the device. And this happens for all the work. You can appreciate the very good agreement between the two approaches. What I want to highlight is that SAP 2000 is finite element model, a 3D finite element model of the whole structure. And the first one, what we computed yesterday within MATLAB, is just a bunch of equations, dynamic equations of a single degree of freedom. But you see how the response is fairly captured. So this is one of the best, I mean, aspects for isolated structures, because with very simple models, you can get a good estimation of the overall response. And for different earthquakes, you see how also the hysteresis is well captured. Also here we have a number of harmonic waves. So we have 1, 2, 3, 4, 5, 6, and then an ending loop, something like an ending loop. So these results allows you to understand how linear devices can be directly associated to an harmonic motion. Whenever we start having something highly nonlinear, automatically we have to reduce the number of let's say cycles to be applied to the devices. And then finally earthquake 1. Okay, I think that we are done with I mean this comparison, so the final goal of today's lecture, and I think this is it also for the whole short course. Is there any question again? So obviously, if you will have some questions also afterwards, the conclusion of this short course, please email me, so we will also can have some conference call to clarify some doubts and so on. I again want to thank you for the interest in this short course. I hope you enjoyed the information, and I hope that all the information that I tried to deliver were clear. Otherwise, please ask, and I will, I mean, available for any kind of questions rather than needs. So I hope we will have also the opportunity in the future to cooperate. And so I just leave you by reminding that there is the final homework that you can send me by email within the next Tuesday at 6 p.m. It is just a very simple exercise, just for you to show that you have clearly understood the topics, the global topics, I mean, that we have covered. So I thank you very much for the interest, and see you, and have good luck for everything in your future.
Thank you, Professor. The course was very good. Thanks for everything.
Thank you. Bye.
Thank you for the course, Professor.
Thank you, Professor. Bye-bye.
Thank you, Professor.
Thank you. Bye.